Good afternoon all. Here I am going to teach you about deadlock detection and recovery from deadlock. So far we have seen system model of deadlock, deadlock characterization, methods for handling deadlock including deadlock prevention and deadlock avoidance. Now we are going to learn about deadlock detection and recovery from deadlock. So deadlock detection. Deadlock detection is allow the system to enter the deadlock state and detect the algorithm, and after that recovery. So deadlock detection algorithm is classified into two division. First one is single instance of each resource type, and second one is multiple instance of each resource type. For single instance of each resource type, we are making one wait for graph, and wait for graph is variation of resource allocation graph. Already we have learned what is resource allocation graph. From this resource allocation graph you can make the wait for graph. After making wait for graph you have to see whether any cycles are there or not. If there is a cycle, that is indicate deadlock is there. If there is no cycle, no deadlock. So here how to convert resource allocation graph to wait for graph. For that, maintain a wait for graph. Nodes are processed pi to pj if pi is waiting for pj. Periodically invoke an algorithm that search for a cycle in the graph. If there is a cycle, there exists a deadlock. Let me explain this points. See here. Take this R1. R1 is assigned to T2. T1 is waiting for R1. So actually T1 is waiting for T2 to complete their task. Once T2 complete their task, this R1 is releasing. So T1 will get the R1 back, right? So if you have a edge like this, T1 is waiting for R1 and R1 is assigned to T2. Then you can eliminate R1 and connect T1 to T2. T1 to T2. Here R3 is assigned to T5 and T2 is waiting for R3 as requesting R3. So once T5 is completed their task, this R3 is returning back to, or R3 is assigning back to T2. So connect T2 to T5. Here also R4 is assigned to T3 and T2 is requesting for R4. So T2 to T3 one connection. And T3 is waiting for R5. R5 is allotted to T5. So T3 to T4 one connection. The same way T4 is waiting for R2 and R2 is assigned to T1. So T4 to T1 one connection. So this T1 to T2 indicate T2 is holding one resources and T1 is waiting for that T2 to complete the task. After completion of T2's task, T1 will get the resources. So this is the wait for graph. After making this wait for graph, search for the cycle. Here T1 to T2, T2 to T3, T3 to T4, T4 to T1. There is one cycle. This cycle indicate there is a deadlock. Then next one is several instance of resource type. Now here we are applying one algorithm, and these are the data structures of the algorithm. This data structure is same as your Bangos algorithm. First one is available. Available is a one-dimensional array or vector. A vector of length m indicate that number of available resources of each type. Allocation and request are two-dimensional array of size n by m, and allocation defines the number of resources of each type currently allocated to each process. Request is a again n by m matrix. Indicate that the current request of each process. If request of ij is equal to k, indicate process pi is requesting k more instance of resource type rj. Let me explain the algorithm in detail. Detection algorithm. There we have two more variables, work and finish. Work is same as your available, and work is initializing with the available, and finish is array, and array size is number of process. And if your allocation is not equal to 0, then initialize finish with the false, otherwise initialize finish with the true. Then second step is you have to see two condition. Finish of I is equal to false, request less than or equal to work. If you are not able to find any process with these two condition, you can step into 4, and fourth step is finish of I is equal to false for some I to n, then the system is in deadlock state. Moreover, if finish of I is equal to false, then pi is deadlocked. If you are able to find a process with these two conditions, go to step 3. Work is equal to work plus allocation. Update your work with the work plus allocation. Finish of I is equal to true. And you have to repeat step 2 and step 3 for number of process. I'll explain the example, then you will get the better understanding of the algorithm. Example is this one. There are 5 processes P0 to P5. P0 to P4 and 3 resources A, B, C. A is 7 instance of A is available, 2 instance of B is available, and 6 instance of C is available. And P0 is allocated with 1 B, and they don't want any more any extra resources. And P1 allocated with the 2 A's and they requested 2 A's and 2 more B's. P2 allocated with a 3A, 3C and they don't want any more resources. And P3 allocated with a 2A, 1B, 1C and they need 1 more A. P4 allocated with only 2C, they need 2 more C's. And currently available resources, see, total 7 A's are there. Out of 7, 2 plus 3 plus 2, 7 are allotted. So currently available A's are 0. Then 2 B's are there. Out of 2 B's, 2 B's are allotted. So currently available B's are 0. Total 6 C's are there. Out of 6, 3 plus 1 plus 2. 6 C's are allotted. So currently available C's are 0. Now you have to apply the safety algorithm. You have to check whether there is any deadlock or not. See, first if you apply the safety algorithm, you will understand. First you can complete P0. After that you can complete P2. Then you can complete P3. Then you can complete P1. Then you can go for P4. So you will be able to generate this sequence. Suppose condition is like this. P2 requests an additional instance of type C. See, P2 is asking for additional instance of type C, 1. So this is the current request. We don't have any available things. So P0 doesn't want anything. So you can complete P0. After completion of P0, they'll be releasing the resources. They had only 1B, right? So that 1B they'll release. And P1 required 2A. We don't have. We have only 1B. P2 required 1C. We don't have. P3 required 1A. That also we don't have. P4 required 2C. No, we have only 1B. So only P0 will be able to complete. P1 to P4 won't be able to complete. So deadlock is detected. Next one is recovery from deadlock, process termination. So how to recover once it is detected? How to recover from deadlock? One method is abort all deadlocked process. You can abort one by one process at a time until the deadlock cycle is eliminated. So in which order we choose to abort? There are many criteria. First one is priority of the process. You can select the less priority process or how long process has computed and how much longer to completion. Suppose one process 99% is computed. So don't select that process to abort. Resources that process has used. Suppose there are shortage of resource type B and current process is not using B. So don't select that process for aborting. Resource process need to complete. How many process will need to be terminated? Is process interactive or batch? Based on all these conditions, you can select the process one by one until the deadlock cycle is eliminated. Then second method is resource preemption. So select a victim select one particular process and based on minimize the cost. And after that, after selecting the process, take the resources back, then roll back that process to safe state. Then that resources you can allocate to another process. So these are the method to recover from deadlock. I hope all of you understood. So here we have explained deadlock detection and recovery. So next video we are moving to memory management. Thank you all.